SwayamPrabha. Digital India. Educated India.
Dear learners, we are in the course Advanced Thermodynamics and Combustion, Module 8, Combustion and Flames. In the last two lectures of the module, we have deliberately discussed laminar pre-mixed flame. Today, we are going to discuss about laminar diffusion flame. Now, in this laminar diffusion flame, we will touch upon the following topics. First one is non-reacting laminar jet, then jet flame mathematical descriptions. Here we will not go deep into the governing equations and solutions, rather we will focus on the end results of those equations, and subsequently we will discuss about the physical aspects. The next important point to be discussed is laminar diffusion flame structure, and one of the parameter which is called as a conjugate scalar, which was introduced in earlier lectures, we will try to see what is this, what is its significance with respect to jet flame. So, let us start. The first thing to give some brief introduction about non-reacting laminar jet. We will see that the laminar flame diffusion flames importance will be realized when we are burning jets of fuels. So, by burning jets of fuel we mean this is something like when the fuel is injected through a nozzle, for example, in a fuel injector in a diesel engines. In such those cases, what happens, there is some diffusion flame is generated. So, basically diffusion flame, when it is generated, it means that fuel and air mixture is pre-mixed to some extent, and again when the jet comes out, it tries to get rest quantity of oxidizers from the air. So, typical example we can see in a Bunsen burner flame, the outer cone of this diffusion flame is nothing but your outer cone is nothing but the diffusion flame, whereas the inner cone is mainly the pre-mixed flame. Now, when you deal pre-mixed laminar flame, the treatment was different. Now, when you deal with diffusion flame, then there are some other issues. It comes as a jet, and the fuel, when it comes out from this nozzle, it or fuel injector, it tries to spreads and it tries to diffuse with respect to air. So, all sorts of phenomena that comes into picture, and in a actual scenario, what happens when the fuel is injected from a nozzle, it tries to diffuse within the air, and side by side the combustion happens. Combustion happens means that density of the mixture keeps on changing within this flame structure or within the flame domain. As a result, equivalence ratio also changes. But what we are trying to analyze here, we will try to see that in a very hypothetical way. We view that as if a fuel jet is being injected from a nozzle and it tries to diffuse in the air, and during this diffusion process, one thing that we are assuming that they are not reacting. That is first thing. Second thing is that during this process they are not reacting. By non-reactive mean that density do not change during the reaction process. So, such a things can be modeled if you assume a constant density reacting mixtures. So, you can choose some fuel and or air, we can choose a fuel whose density is also similar to that of air, similar number with that of air. So, such analysis will tell us, without combustion being happened, it will tell us that how this jet behavior when it comes out, and when it how the jet spreads, how the jet diffuses, what is its spreading rate, and how the mole fraction, mass fractions or fuel fractions changes along the axial length of the jet. All sorts of things is the discussion pattern or discussion of these lectures. So, first thing that we say, we need to emphasize that laminar diffusion flames are very important, and it finds many applications. One application I said in the diesel engine, in some cases in the gas applications, in cooking stoves also, we use partially premixed air to provide non-shooting operations. Here one more important point is that we intentionally provide a partially premixed mixture to the air just to provide a non-shooting, that means soot does not form. That means it has mixing has taken place earlier, and when it sees the oxidizer, fuel tries to combustion is to happen without having any unburned products. As I mentioned, the familiar example of a non-premixed jet flame is the Bunsen burner outer cone flame. In our study, the prime concern of these laminar jet flames is to discuss about the flame geometry with short flames and fuel types. So, before entering all those such things, the important discussion that we need to emphasize here, we are going to consider a laminar constant density jets. Constant density jets, I mean that in a combustion systems we have a fuel and oxidizers. Normally oxidizer is air, and air has certain density at given conditions of pressure and temperatures. So, we are choosing a fuel whose density is of similar number with respect to air. So, in that way we can say it is a constant density mixtures, and assuming that by doing so we are also saying that it is non-reacting. So, that means if you simulate the actual behavior, density keeps on changing after during this combustion process, because the products are formed. But when you say constant density, we assume that it is a non-reacting, but we are choosing a fuel such a way that we can get the behavior is analogous to the actual jet flame. So, through this analysis, it will be possible to establish the general characteristics of velocity, nozzle fluid concentrations fields of laminar jets, and understand the Reynolds number dependence of spreading behavior of the jet. So, we will look into nozzle fluid concentration diffusions, which is identical for equal flow rate, which translates to frame length based on the flow rates for a given fuel oxidizer combinations. Let us see how the things we are going to discuss. So, what we are considering is a simple case in which a laminar jet of fluid, that means fuel, which flows into an infinite reservoir of quiescent fluid oxidizer. So, if you look at this particular figure, we are seeing that a fuel which is getting injected through a nozzle of radius 2r of diameter 2r, and it goes into it comes as a jet, and when it comes as a jet it tries to spread, and the outer medium is nothing but your a stagnant fluid, and in this case it is oxidizer or nothing but air. So, if you say the nozzle of radius r, and the jet that comes from a fuel jet that comes from a nozzle of radius r, and it enters into a still air, the velocity profile is assumed to be uniform at the nozzle exits. So, this one assumption we are making, saying that at the nozzle exit, that means at x is equal to 0, that is nozzle exit, at that point your will have a velocity profile will have uniform, and during what happens during this, now when jet comes, we will have a potential core, and that potential core lasts for a distance x c, and this is nothing but a initial cone, and the tip of this cone is nothing but the axial distance x c from the exit of the nozzle. So, this is something to the similar to a fully developed flow in a pipe. So, what we say is that there is exists a potential core closer to nozzle exit, in which the presence of viscous shear and diffusion is not felt. That means, within this potential core the fuel moves freely without any viscous dissipation or diffusion, and in fact, it has sufficient momentum. The nozzle fluid mass fractions velocity remains unchanged from this nozzle exit value, and they are uniform. Now, what happens outside? So, what we are looking at, we are saying that if this is the 2r is the diameter of the nozzle, and this is the axial distance x which we are looking at, and if you take two arbitrary locations x is equal to x1 and x is equal to x2, and if you try to plot what is the value of the ratio, one is fuel mass fraction and other is the velocity at any x with respect to velocity at x is equal to 0. So, this at x is equal to 0, this represent V x 0 velocity, and at any x we say it is V e exit velocity at any x. And if you try to plot, what we can see, it starts with 1, that is, and we, if you keep on going along the axial distance, its value drops. And then another way we can represent that what happens to fuel and what happens to fuel mass fractions at the two different locations. So, at x is equal to x1, okay, first thing let us see at x is equal to 0, we have radius r, and it is whether you take the velocity ratios at x Vx by Ve or fuel mass fractions, they are 1. But when we go at any x, so what happens? This value keeps on changing. So, Vx by Ve or Yf, this value monotonically comes down. So, at maybe at x is equal to 1, its value was initially 1, but at x is equal to x1, it has come down to this value. And even at if we further distance at x is equal to x2, this value again further drops. So, there is a monotonically drop in the velocity ratios, fractions and fuel mass fractions. So, we will try to quantify how I mean what rate or what is the mathematical background behind this. Another important point needs to be emphasized, that when the fuel comes out at the initial point, that is x is equal to x0, it has a sufficient initial jet momentum, and with this jet momentum it tries to penetrate into the air, and when it penetrates with distance, its momentum tries to drop. So, these are the reasons that why the velocity ratios drops, and even the fuel concentration also drops. But one thing that we want to see is that again if you look at the radial distributions, that means at any x is equal to x1, there is a radial distribution of this fuel jet. So, this radial distribution and axial distribution of this fuel jet, we are going to understand how they behave. Another important point is that similar to the flow through pipe, we have a central line velocity and we have velocity at the wall. In the same situations, we can say that when its fuel comes out, it as a jet, and there is a what we can say non-physical boundary, and that boundary called as a jet boundary. So, these are the jet boundaries that comes out when we refer this as a jet boundary. And of course, there is no existence of a physical boundary as it is there in the pipe flow, but here it is a jet, I mean it is just a non-physical boundary across which the property informations of the jet as well as the air that tries to match. And during this while deciding this jet boundary, we try to see that in this zone we have mostly it is concentrated with fuel, and we have other side of this jet we have mainly with air, and the boundary is to be regulated with respect to the property value or matching value between this fuel and air based on these conditions, that how fuel propagates into this medium. So, what we can see is that the fuel air tries to penetrate towards the fuel and fuel tries to diffuse towards air. So, this phenomena actually decides the boundary of the jet. Again, while talking about the fuel mass fractions, it is known that because of high concentration of the fuel in the center of the jet, the fuel molecules tries to diffuse outwards and with respect to Fick's law. Now, effect of moving downstream is to increase the time available for the diffusion to take place, and through this process the width of the region of fuel molecule grows with the axial distance, and the central line fuel concentration decays in a similar manner with respect to fuel velocity. So, basically both velocity and fuel mass fraction or fuel concentration decays. Now, let us see how we are going to model. What we are trying to say is that momentum of the flow set by any axial location is same as that of momentum issuing from the nozzle exit. So, it is nothing but the momentum balance or force balance. At any exit it should match. Similarly, mass of the fluid issuing from the nozzle is conserved with respect to mass fractions as unity at the nozzle exit. Another assumption we make that the momentum and specific diffusivities are constant and equal. So, that is a momentum of the flow, and at the same time there is a diffusion of species across the axial as well as the radial directions. These two parameters is governed through a non-dimensional number, and we call as a Schmidt number, and it expresses the ratio between this momentum and species diffusivity. So, basically we have two species, fuel and oxidizer, for our analysis, and based on that we need to frame the mass conservation, species conservation and axial momentum conservations. And here since we are looking at the axial distance as versus the radial distributions, appropriate coordinate system would be the cylindrical coordinates. So, based on that the three equations were derived. Here we have only axial velocity dou v by x dou x plus 1 by r into dou r b r by dr. So, Bx and Vr is nothing but the axial velocity and radial velocity. Similarly, we have axial momentum equations and we have species conservation equations. Side by side we also define the mass fractions of fuel and oxidizers, and here we also have another equation which another number, Schmidt number Sc is defined by nu by d, where nu is the viscosity and d is the diffusion coefficient. Now, let us see how we understand these boundary conditions. So, basically there are two things. One is this is central line, and this is at x is equal to 0, and central line means it is r is equal to 0. So, we are looking r in this direction and we are looking at x in this direction. So, this is x and this is r. So, what happens at central line r is equal to 0, we have Vr at central line is 0, corresponding its Vx dVx by dr is also 0, and mole fraction is also 0, differentiation of dyf by dr is 0 because it is a fixed value. At r is equal to very high, means very larger radius, means if we are looking at sufficiently larger radius, fluid is stagnant. So, as if there is no fuel present. So, under those conditions your Vx at r is equal to infinity is 0 and yf also at r is equal to infinity is 0. And again at the jet exit means at x is equal to 0, we have two possibilities, either we can r less than r or r can be greater than r. So, accordingly we have exit velocity V or exit velocity when r greater than 0 is equal to 0. So, this also can be interpreted for fuel fractions as well. So, fuel concentration at the YF are less than equal to 0 is YFE, that is exit concentration of fuel fractions, and beyond r greater than 0 its value is 0. Another point that needs to be emphasized, that momentum of the jet at any x. So, at any x is defined by j is equal to twice pi rho into v square into r dr, and which has to be integrated from 0 to infinity, and that has to be equalized with respect to momentum, jet momentum at x is equal to 0, that is initial jet momentum. Similarly, the fuel mass fractions has to be equated, fuel mass has to be can be calculated with respect to its value at x is equal to 0. So, this is the very basic bottom line through which these equations needs to be solved, and ultimately we are not going to into derivations for this, but what we are going to find is the solutions for this. So, while talking about the solutions, we are talking in terms of ratios. First ratio is the non-dimensional axial velocity distribution, that is Vx by Ve. So, I mentioned that V is the exit velocity, Vx is the velocity at any x. So, if you say this is x is equal to 0, we are talking about Vx at any x, and that is a function of two parameters, that is non-dimensional axial location, that is x by r, and other parameter that is known as similarity parameters. Why there is, what is the importance of similarity parameter? Because we are looking at the velocity distributions as well as the fuel mass fraction simultaneously. So, the similarity parameter that controls both the parameters simultaneously is defined by zeta, and this zeta is nothing but is correlated with respect to viscosity r by x and jet momentum at the initial momentum rho e, and this with this similarity parameters we try to derive the expressions for the non-dimensional axial distributions for velocity and fuel mass fractions. So, if you see these expressions here, we have one equations, they have, if you see both the expressions, one similar some solution is that their expressions are almost same or same. So, that is the reason, if you can see, the decay for velocity distribution and fuel mass fractions almost are exactly same in nature. And from these equations we can find out the central line velocity as a function of Reynolds number and axial locations. We can also find out the central line mass fractions, which is typically needs to be the highest, and with x as well as r they are going to decay. Another term Reynolds number, that is calculated based on the radius of the jet rho e v r by mu, and we also know the initial momentum of the jet because you know the exit conditions of density and velocity, and we also know the radius of the nozzle. So, from this we can find the non-dimensional form of velocity ratio and fuel mass fractions. But however, when deriving the solutions, it is always taken care it is valid far from the nozzle for these conditions, but however it gives a more or less similar physical nature of the actual situations of jet plane. Okay. Now, this particular plot shows the non-dimensional central line velocity with respect to axial distance. So, we are looking at the axial distance x and its dependence with Vx O by Ve. Vx O by Ve means at this location is Vx O and Ve is any location, that ratio x, that non-dimensional ratio. So, this ratio is plotted against axial distance. We see that when the Reynolds number is increased, what happens, the decay is okay. In other words, I am saying the decay is more rapid when the Reynolds number is small. That means, if you come back the other directions, instead of going up, if you come back from decreasing order of Reynolds number, the decay is faster, whereas decay is slower, because you can see the distance decay is as a very faster rate, maybe 10 times, 100 times, 1000 times. So, if you say that lower Reynolds number of jet has higher rapid velocity decay, and this is occurs because the relative importance of initial momentum becomes smaller in comparison with the viscous shearing action. The next parameter that we are looking at is the jet spreading rate and the spreading angle. So, we define this jet spreading rate with respect to jet half width. So, what does this mean? That if you plot the non-dimensional velocity with respect to radius, that means along this radial profile, we find that at one particular locations, that is r 1 by or jet half width, we will find at r half where this value, this ratio value drops from 1 to 0.5, means the ratio of jet half width to the jet axial distance is referred as jet spreading rate, and this jet half width is defined as the radial locations at which the jet velocity has decayed to half of its central line value. So, once we know this jet spreading rate, we can find the jet spreading angle is the angle whose tangent is the jet spreading rate. That things we can represent in mathematical form as jet spreading rate is equal to r half by x, that is by definition it is defined by this, and this is equal to 2.97 Re to the power minus 1. So, this says that if your Reynolds number is high, then jets are narrow, while the low Reynolds number jets are normally wide. So, this information gives the how a jet spreads in the oxidizer, or how the fuel spreads in the oxidizer. The other important aspects of laminar diffusion flame is to find the length of the flame. So, if you look at the actual scenario, we will see that we have different zones, and that different zones normally represent the concentration of fuel and air ratio. Some location, that means toward in the vicinity of the potential core or towards the nozzle side, I can say towards the nozzle side, we can find equivalence ratio is more, and as and when we go along x, we will see that equivalence ratio keeps on coming down. So, when it keeps on coming down, it means that we are reaching towards more towards the air zone, and one particular, and in fact the flame surface or what we say the zone is normally decided by a surface that normally tries to see the regions in which air and fuel they are equal, the air and fuel properties match, and one particular point or one particular flame zone where we can find there is a phi is equal to 1. So, it means that at the entire contour of this flame zone or entire locations on this flame zone, if you calculate the equivalence ratio, they are equal, which means that complete oxidation or complete combustion has taken place on this particular flame surface. Now, if you look this particular surface, it is not a case of complete combustions. In this zone, we will find there are some fuel particles still they are not burnt, and when you move beyond this flame zone where or phi is equal to 1, we will find there are we have sufficient oxidizer, but there is no fuel to be burnt. This mismatch tells us that there is a particular length what we call as x is equal to LF, that is the length of the flame, and that length of the flame is calculated as axial distance from this exit of this nozzle, and that x is equal to LF, and that is nothing but the flame zone where which is defined that there is more beyond this length, which means that beyond this length there are enough oxidizer in the surroundings to burn the fuel completely, but below this length there is not enough oxidizer. And normally when you talk about this flame surface, it is nominally defined as the contour where fuel and oxidizer meet in the stoichiometric proportions, or in other words we say that flame surface is the locus of points where the equivalence ratio is equal to unity. So, this is the catch mark point where which needs to be known, and for every flame situations or every laminar diffusion flame we need to calculate this flame length. So, this flame this contour is normally defined by these expressions in terms of equivalence ratio, that is phi, that is r is equal to 0 and x is equal to LF is equal to 1. Now, while talking about this flame length, we will also have flame width. There are two phenomena that takes place here. We talked about flame length, let us talk about what is flame width. Flame width means if you go along the length of the flame, we will find the effect of buoyancy. So, basically the buoyancy accelerates the flow that causes the flow to narrow. So, when the fuel gets pushed up towards the air, so the flame tries to be narrow. At the same time, when the flow becomes when there is narrow flame, it increases the fuel concentration gradient and enhances the diffusions. So, basically fuel tries to diffuse outwards, at the same time buoyancy also pushes up. So, the buoyancy pushes up and fuel also tries to diffuse outwards. So, this combined two effects gives such kind of surface, and that surface we call this as a flame surface. And one particular surface at we can find for phi is equal to 1, and for that phi is equal to 1 we can find a particular x, that at what x it appears. So, that is nothing but x is equal to LF. So, the length of the flame is decided based on these two parameters, one is buoyancy, other is the diffusion. Another significant part of this flame is what we can say soot formations. So, formation of soot in a flame. We already told that when you see the flame surface below this phi is equal to 1, this is basically all the surface have equivalence ratio more than 1. So, that means they are rich in fuel, but they do not find sufficient oxygen or oxidizers. So, this causes that there are some unburnt fuel particles that remains. Now, when we say when you look at this particular figure, these unburnt particles leads to the formation of soot, and we call this as a soot formations, and this soot formation normally initiated at the exit point of this nozzle. So, in the maybe starts with a potential core, and because of this momentum of this flow and the soot particles tries to move up. So, basically through this process what we see is that we have soot particle inception zone, then there is a zone what we call as soot particle growth zone, and the soot particles tries to oxidize, and if they are sufficiently oxidized, there is no further possibility. This is a normal convention that even if during its propagation the fuel particles has oxidized. Now, if at all for variety of reason if it does not, then what happens, we will have a formation of soot wings. In these soot wings, that we will find some zone at some flame surface, we will find there is a soot breakthrough. That means these soot particles try to break, and that when they try to break, and we normally refer this as a smoke. So, depending on the fuel type, fuel residence type, not all the fuel gets oxidized during its journey from high temperature regions. So, many a times soot wings are formed, and which refers as breaking of soots through the flame. The soot that breaks through the flame is referred as the smoke. And last point that I need to emphasize, that from this understanding of our analysis or mathematical expressions, one can find out the length of the flame for which phi is equal to 1 as approximately equal to 3 by 8 pi into QF divided by dF into Y stoichiometric, where QF is nothing but the initial volume flow rate, and that is decided by the initial jet velocity and area of the nozzle jet or nozzle port. Then D stands for species diffusivity, BE is the velocity of the fuel at the port exit, and YF is nothing but the stoichiometric fuel mass fractions. So, it clearly tells that length of the flame is directly proportional to the volume flow rate and inversely related to the fuel mass fractions. The other important aspect that I need to emphasize is the conserved scalar. So, the conserved scalar is a quantity or which is normally used in all types of combustion problems, which says that any scalar quantity that remains conserved throughout the combustion process. One such parameter is nothing but the mixture fractions, and the fraction of mass or mole fraction of the component which originates from the fuel and which remains conserved throughout its journey in the combustion process. So, based on that, what we see is that if you look at a flame sheet, we can have 3 distinct locations. One is on the flame surface, where F is equal to stoichiometric value. At that point, your mass fractions is almost exactly entire combustion has happened, and Y products are is equal to 1. And when you within this flame, we will find there is some mass fraction of the fuel as some products. Outside the fuel, we will not find fuel, we will find oxidizer and products. So, there is a misbalance between the flame surface or flame sheet inside the flame and outside the flame, and distribution of temperature and mass fractions can be represented in this manner, as it is a very clear understanding that temperature keeps on increasing till stoichiometric value again further drops with respect to fuel fraction, fuel mass fraction, and if you see the mixture fraction value with respect to the mass fraction Y, then for oxidizer, for fuel and products, then it can be plotted at that fuel stoichiometric value, its value is mixture fraction is 0. So, a complete understanding we can make what happens. So, by definition we can say a mixture fractions is the fractions that of the mass of the material that originates in the fuel stream divided by mass of the mixtures. This is by definitions. So, based on that we have fuel fractions, we have the fuel stoichiometric value when 1 kg of fuel mixes with mu kg of oxidizer to form mu plus 1 kg of products. So, we have 3 distinct zones, one is inside the flame, and under that conditions based on these relations we can find within the flame what is the mass fraction of the fuel, what is the mass fraction of the oxidizer, and what is the mass fraction of products. Similarly, outside the flame we can find what is the mass fraction of fuel, oxidizer and products, and that relations we can represent in terms of stoichiometric values. So, this is all about I have discussions with respect to laminar jet flames. So, based on our understanding, let us try to solve some numerical problems with respect to jet flame. So, the first problem that talks about we have a jet of ethylene, that means ethylene jet that comes out of a nozzle, and that nozzle diameter, that 2R is 8 mm, and the ambient conditions that comes out is air, and air condition is 300 Kelvin and pressure is 1 atmosphere. So, under these conditions we need to find out the spreading angle and two parameters. Basically, we need to find the spreading angle, other is we have to find the axial location, where at which the jet central line mass fraction drops to the stoichiometric value. And all these things we need to find out for two velocities, one is 0.08 meter per second, other is 0.008 meter per second. So, basically we know VE1 as 0.08 meter per second and another value is VE2 we have 0.008 meter per second. For these two conditions we need to find out jet spreading angle and axial locations. So, let us start the solution. The first thing that we need to check whether it is a constant density or not. So, constant density I mean if you look at ethylene. So, ethylene is C2H4 and its molecular weight is 28 and molecular weight for air is approximately 29. So, more or less we can say a constant density situation may be assumed, and again it is a non-reacting when you say constant density, non-reacting also will have similar resemblance. So, considering this, that whatever mathematical treatment we have done for this study, we can make use of that. First thing that one need to calculate is what happens to spreading angle. So, spreading angle is defined as alpha, and that alpha is nothing but tan inverse r half by x, and this r 1 by 2 by x is nothing but 2.97 by r e j. So, this information you require. The first thing that you need is what is Reynolds number. So, Reynolds number for the first case we can write rho VE1 r by mu. So, mu is given 102.3 into 10 to the power minus 7 Newton second per meter square, and rho we can find out for air. For this atmospheric pressure and 300 Kelvin, this can be assumed to be 1.15 kg per meter cube. So, we know rho VE1 first case is 0.08, r is twice r is 8 mm. So, r means it is 4 mm. So, putting this value we can write 1.14 into 0.08 into 0.004 divided by 102.3 into 10 to the power minus 7. So, this number is 35.65. Now, second case RE2 will be rho VE2 R by mu. So, this number would be just scaling difference. So, it will be 3.565. Now, when you have this, we can find for the alpha 1 first case would be tan inverse 2.97 divided by 35.65. So, this angle is 4.75 degree, and alpha 2 second case will be tan inverse 2.97 by 3.565. So, this number is 39.8 degree. So, it sees that the low velocity jets means low Reynolds number jets implies higher spreading angle. Okay. So, this information we get, that is also naturally true. And the second part of the discussion would be, we need to find out the spreading angle and axial location of the jet central line mass fraction when the jet drops to the stoichiometric value. So, for that we need to find out the expressions what when you say yf stoichiometric, and that is equal to yfo, that is at this x is equal to 0. That relations we have, if you recall, that is 0.375 Rej into x by r and to the power minus 1, and this will give you x is equal to 0.375 Rej divided by yf stoichiometric into r. So, basically we need to find what is the y stoichiometric values. All the other parameters is known. R is 0.004 m, Rej you know, Re we have Rej1 and Rej2. So, what to find this stoichiometric value, we have to recall this fundamental equation Cx H y plus A O2 plus 3.76 N2 gives rise to x CO2 plus y by 2 H2O plus 3.76 A N2. So, from this for ethylene we write it is C2H4, that means x is equal to 2, y is equal to 4 and A is equal to x plus y by 4, and that number is 3. So, when you know all these things, we can write the stoichiometric value, that is air fuel ratio stoichiometric is equal to m air by m fuel, and that expression is 4.76 A molecular weight of air by molecular weight of fuel. Then from this we can find out the number, as we know air and fuel molecular weight, we can find out this number as 4.76 into A is 3 into 28.85 divided by 28, or simply we can write 29. So, this number will be 14.7. So, y stoichiometric would be 1 by 14.7 plus 1. So, this number is 0.0637. Once we have the stoichiometric value, then we can find the two parameters. One is x1. x1 would be 0.375 into Rej1. Rej1 is 35.65 divided by 0.0637 into R is 0.004. So, this number would be 0.84 meter. Similarly, x2 would be 0.375 into 3.575, that is Rej2 into 0.004 divided by 0.0637. This would be 0.084. So, it says that fuel concentration decays to same value for low velocity jet with respect to high velocity jet. Okay. And next is the same problem, but it is tuned in a different way, saying that here we are looking at data that is given is BE1, which is 0.008 meter per second, twice R is 1 is 8 mm. Now, what is required is we have to find out the exit diameter of another of the nozzle, which is required to maintain the same flow rate. Flow rate is to remain same, but exit velocity. So, BE2 has to be increased 10 times. 10 times means 0.08 meter per second. So, here the exit velocity is increased by changing the radius of the nozzle. So, for that what remains same is the flow rate, volume flow rate. So, we can say flow rate Q remains same, that is VE1 into A1, that is equal to VE2 into A2. So, from this expression we can find out a relations that VE1 into pi R1 square is equal to VE2 into pi R2 square. So, this means R2 is equal to VE1 by VE2 into R1. R2 square is this, VE1 by VE2 into R1 square. So, we know R1, we know VE1 by VE2. So, from this R2 can be found out as 1.2 mm. So, this gives twice R2 or diameter of the nozzle, exit diameter of the nozzle as 2.4 mm. So, to maintain this flow rate, the exit diameter has to be 2.4 mm. Now, for this situation we need to find out the axial location for which fuel mass fractions drops to stoichiometric value. So, we again for this nozzle we need to find out what is Reynolds number of the jet. So, it is rho BE2 into R2 divided by mu. So, rho is 1.14 or 1.15, BE2 is 0.08, R2 is 0.0012 divided by mu, it is 102.3 into 10 to the power minus 7. So, this number is approximately 10.7. Then we can recall that expression x is equal to 0.375 REJ divided by YF stoichiometric into R. So, this number would be 0.375, REJ is 10.7 divided by x stoichiometric value is 0.0637 into R. R is in this case is 0.0012. So, x is approximately 0.075 meter. Okay. So, so this is almost close to the previous cases of x value is 0.084 meter. So, this is all about the discussions for today. Thank you for your attentions.